everyone. We start our departmental seminar, and I'm happy to present Professor Jason Morgan from the Earth Sciences Department of the Royal Holloway University of London. Main research interests of Professor Morgan are geodynamics, subduction, zone dynamics, serpentinization, melting, and hydrothermalism. Influence of serpentinization on geologic timescale, carbon and methane cycling, and early atmosphere oceanochemistry. Computational geodynamics, 3D viscous flow, mantle melting, and visualizations, 3D hydrothermal flow, fluid drop interaction and visualization, and geochemical and rare gas evolution of the mantle. Professor Morgan participated in 20 research cruises, and 11 from them are as a chief or co-chief scientist, and was awarded by numerous prizes and awards, like prestigious James McElwain Award of the American Geophysical Union. Please.
Thank you very much. I somewhat apologize. You asked me for CV, and I sent what I give for proposals in the UK. So, like the research interests, I am very much interested in sort of how the larger scale part of how our planet is working. And today I'm going to talk about an idea that I think might be very important for what goes on at subduction zones. And it's the chemical reactions that might happen when one of the tectonic plates is bending. And thank you very much for inviting me. My wife actually got invited to give a talk here also. And when I heard she was going to Israel, I said we have to make a family vacation. And then I'm real happy that I can also do a little and see a little science as well on this trip, not only the trip of a 7-year-old child. Okay, I'll get going. And if you have any questions, please feel free to. This can be somewhat informal. And so just to set this up, you probably have heard people talking about the global carbon cycle, and over geologic timescales, there have been some simple box models made. Maybe some of the most famous have acronyms like BLAG, like burners, and lasagna. And they talk about the biggest fluxes in the carbon cycle once you get beyond biomass, the annual biomass cycle with plants, are things related to the precipitation of carbonates, the erosion of carbonates, volcanic fluxes from arcs in particular, and deep sea burial or marine carbonates. And then the very long-term flux that people talked about was something and I'm talking now there's two sets of units. I'm going to use moles. Maybe more important, this is 12 and this is 1.5, where the width is proportional to the amount. Mid-ocean ridges are thought to be emitting about 1 to 2 teramoles a year. And this is thought to be sort of the main outgassing from the deep interior of the planet. I think this number probably should be revised upwards, because I think ocean hotspots play an important role and haven't really been quantified as well as ridges. But then in addition, what I'm going to talk about here is that there may be a very important carbonate sink that happens when the plate is bending. So that we know a lot about the hydrothermalism that happens at mid-ocean ridges and the very slow hydrothermal flow that happens off axis. But there is this newly recognized process since sort of 2000, it's been recognized, that when the plate is bending, you may have the opportunity that you have relatively cold lithosphere. This is a very crude picture of the crust. So you have relatively cold mantle, less than 600 degrees. If you can provide a mechanism for seawater to reach that mantle, it will start to serpentinize. So at a mid-ocean ridge, it's very difficult to serpentinize a lot because everything is so hot. You just don't get very deep. You can only you can talk about serpentinizing maybe a kilometer below the moho and maybe more at fracture zones. But where the plate is bending, you may have a process where everywhere along the subduction system, we are having this big chemical reaction. And that's what I'm going to be talking about. And I'm going to show an example where I think it actually is what helps plates to bend and then unbend, basically make subduction possible. And then also that it helps as a major sink in the global carbon cycle, meaning that the global carbon cycle might be tied to phases of when we make new subduction systems, things like that might be correlating with the carbon cycle. So to review the deep volatile cycles, water and carbon, the crude picture is you have outgassing, commonly thought to be happening mainly at mid-ocean ridges from the deep mantle. And then you have the hydration, or the ocean plate going back into the mantle to regas the mantle at subduction zones. And around the end of the 1970s, people discovered these amazing black smoker systems associated with the volcanic systems at mid-ocean ridges. So high temperature alteration of the crust and maybe down to the moho, the uppermost mantle at the moho at mid-ocean ridges. Then you have it's been long known that you have the deposition of deep sea sediments with quite a lot of fluids, quite a lot of chemically bound water in them. And you have the alteration of the ocean crust right at the mid-ocean ridges. And so people before 2000 would make maybe a profile of the water coming back into the subduction zone, and they would say we have sediments with a lot of water, we have the pillow basalts of the ocean crust and the sheeted dikes with a couple percent water by weight. We have the gabbros of the ocean crust, which have less than 1%, but still significant amounts of water. And then they had a picture with dry rocks. And now there's significant evidence that as the plate is bending, we are having a secondary metamorphic reaction happening where we are hydrating or partially serpentinizing this bending plate. And the mantle, for at least 5, 10, maybe 20 off Japan, 30 off Japan, kilometers, we're having partial serpentinization of the mantle, which can be having a significant flux of water. And to give a sense of the number, this unit is saying that beneath each square meter of seafloor entering the trench, we have on the order of 5 times 10 to the 5th kilograms of chemically bound water that's going back in the subduction zone, where 2/3 of this, or even as much as 3/4, is associated with a serpentinization. And this, in fact, is the dehydration of this subducting serpentinized plate is probably the main source of the water that drives the flux melting at island arcs. Here's where this was first documented with direct geophysical methods. So offshore Central America is just it happens to be a place where the abyssal hills of the incoming plate are essentially parallel to the strike of the trench. So this is Nicaragua, this is Costa Rica, Panama would be right down here. And these abyssal hills actually start to refault. They are reactivated. They are almost exactly parallel to the strike of the trench. They get reactivated as subduction progresses. And so here with shaded relief, you can see some of these faults. They go about 50 kilometers at the surface. Seismically, we see them going into 18 kilometers deep, and then we stop seeing them because there's a seismic multiple. It's not that we stop seeing them, they could well go deeper. And you can see that there are quite a few of these that have these very long traces, a couple hundred meters of throw, and they're really prevalent right offshore Nicaragua. And as you go down in Costa Rica, right here is where the aseismic Cocos Ridge is subducting. In fact, Paolo will be talking about this tomorrow. And here, where you have this very thick ocean crust and subducting ridge, you don't see this Bend-Faulting. So this faulting that's happening when the plate is bending, I'm suggesting we should call it Bend-Faulting. And I know, unfortunately, in structural geology, we have fault bend features, but anyway, the faulting as a plate is bending, I'm gonna call it Bend-Faulting. And this is the kind of seismic evidence for this. This is the cross sections right that I just showed you before, and these are MCS profiles. Here are, with the black lines, are two of these bigger faults that continue more than 50 kilometers along strike, and they're present in both this line and this line. You can see the throw at the surface, even in these seismics. You can see them going through the crust, and these little white dots are showing the crust mantle boundary, the moho. And you can see this very high reflectivity in the mantle. So you see very, very high seismic the figure is terrible. But if you go to the paper in Nature, it's a bit better reproduced. But you see this very high reflectivity, and it's actually strongest in the mantle and not quite as strong in the ocean crust. Although you do see some of these faults going through the crust as well. And in order to, this type of reflectivity is not seen in normal marine seismics. So if you go away from where the plate is bending, usually the mantle is pretty boring. You see the moho, you see some reflectivity in the crust, and you don't see very much in the mantle at all. And here instead you saw this very pronounced reflectivity. And the suggestion is that this reflectivity is present because what we're seeing is the seismic contrast between serpentine and mantle, where serpentine has a very strongly different velocity and density than the mantle. And I forgot to show you all the pretty lines, which would have made it easier. Now the reason that this had not been seen in the beginning, just as an aside, in the past, all academic ships had seismic streamers that were relatively short. And these lines that I just showed you happened to be collected by the German Geological Society, the BGR, and they happened to use an industry ship that had a 6-kilometer streamer. So there was no fancy processing. It just happened to have a very long, it was the one survey that had a longer streamer than general. Nowadays, lots of ships are now using 6-kilometer streamers. But in this particular case, if you only have the short offsets, you do not see nearly as much of the mantle reflectivity. It's only when you get the long offsets between 3 and 6 kilometers that you really see these dipping reflectors. So we think that's why it had not been seen before. And as I sort of alluded to, serpentine is a very major transformation of mantle rocks. If we sort of brutalize mantle geochemistry, we can say that peridotite is a combination of olivine, here's magnesium olivine, and orthopyroxene. This is the wrong percentages, but you take something that's 1 unit of each, 1 mole of each, and you add 2 moles of water. In terms of volume, you're taking a cubic meter of rock and adding a half a cubic meter of water, and you end up making something that's about 1.5 cubic meters of serpentinite. That the hydrogen and the oxygen go to be making these planar bonds. It's sort of like a mica. And they're chemically bound in the rock, and the rock is quite slippery. And anyway, you probably have seen serpentine before. And if you want to think about it mechanically, this is 13% water by weight. It's about 40% water by volume. And the way the bonds are, the water is almost behaving like it was just ice. You can think of it, because these are hydrogen-oxygen bonds here, you basically are sticking ice bonds into the structure of the silicate. And so that's why it has such a low density, and it has very has a very, very big impedance change. So the product of density times heat wave velocity between serpentine and mantle, it makes bright reflectors. As you go and partially serpentinize a mantle from 0% serpentine to 100%, there's basically a linear reduction in velocity, where this would be the velocity of pure serpentine, 4.5 kilometers per second, and mantle rock is 8 kilometers per second, and there's a fairly linear change, and the same in S velocity. Density changes by about a third, because, yeah. And the other thing just to keep in mind is serpentine, these hydrous minerals are only stable when the temperature is less than about 800 degrees Celsius and 600 for serpentine, and when the pressure is less than about 230 kilometers depth. So serpentine, because it's so low volume, as you go deep enough in the mantle, it no longer becomes favored because it's so low density. And if you go hotter than about 600, you don't have serpentine, although you can have things where chlorine is substituting for OH, and it can be stable to a slightly higher temperature. And that's what, so chlorite is like serpentine, except that instead of OH molecules, you have chlorine atoms. But so at a mid-ocean ridge, temperatures are much too hot. You don't make serpentine. In a subducting slab, if you have any serpentine and you bring it below 220 kilometers, you're going to lose it. So it's only present under certain conditions. Now, this again is a cross-section in Nicaragua, where the Geomar group decided to try to look at whether there was a seismic velocity change, where this Bend-Faulting was happening. And this is away from the Bend-Faulting, going to the trench. Here's where the Bend-Faulting is significant. And they're seeing a reduction in the seismic velocities, in particular in this area. So normally the mantle, this red line, would be away from the subduction zone. The seismic velocities are 8.1 to 8.4. And in this area here, we're getting seismic velocities right below the moho that are consistent with about 10 to 20% average serpentinization. So the picture that I would have is that you have these faults. These faults are associated with intensive serpentinization, but the faults and their associated damage zones are maybe only forming 20% of the total volume. So 100% serpentinization on 20% of the volume, kind of picture. And the seismic refraction is doing the average. This has been redone in a much better way by a US-led expedition that again went to the same place and shot something going parallel to the coast through the highly bend-faulted area. And they basically find evidence. This picture is a little bit misleading, simply that these plots here, I don't show it. This is number 6. 1, 2, 3, 4, 5, 6. So right here, where this arrow is to this arrow, that's what you're seeing in this picture. So you're only seeing this section here. You're not seeing here, where in fact there is significantly less serpentinization. And down here, there's no Bend-Faulting at all. But you even are seeing here that there's a change in the amount along strike from something that's a little bit less deep serpentinization to even higher in the north. But in any case, they found evidence of significant serpentinization in the same place that the German expeditions had found it. And since this time, this has been somewhat well documented now in offshore Chile. It has been documented off of offshore Alaska by a Lamont group in Donna Shillington and co-workers. The Japanese are actively trying to do this. I was on a cruise in November. The only problem is to do it right with seismic refraction. You need OBSs in Japan that can go deeper than 8 kilometers, and they've had the Japan Trench. You have to put instruments right on the trench, and they're doing it this month I was on a cruise in November where we tried to do it, and with German instruments, and we basically failed. So now the Japanese, having resources that we can only imagine, 4 months later, they're doing it again with Japanese instruments, and I hope they succeed this time. There is, however, indirect evidence offshore Japan, and this, in fact, is where this suggestion that deep serpentinization existed was made by Simon Peacock, right around 2000. He wrote I remember this because I was thinking exactly on these ideas, and it was one of those things that you open a journal and see someone who has published something that I have abstracts in the year that he has a publication. But that's life in science. We were coming at it different ways. But what he noted was he suggested that in the double benioff zone, which is best known in Japan simply because they have the most seismic stations here. I mean, they have by far the best seismic network over a subduction zone. He suggested that this double benioff zone was due to the dehydration of serpentinite, which meant that the serpentine had to form somehow. And one of the mechanisms that he suggested was maybe as the plate was bending. He gave 3 hypotheses. But the evidence was, this is evidence that it exists because we're seeing this would be the dehydration of the ocean crust and basically the contact between the downgoing plate and the overriding plate. And this seismic zone would be the progressive dehydration of the serpentine. And if you look at the width of the double benioff zone in a large number of subduction zones, where this is plotting the age of the subducting plate, so Japan is over here on this plot, you can see that it pretty well correlates with sort of a 300-degree isotherm, 270. And this actually correlates when you try to make crude models of reactive hydrothermal flow. This correlates where the serpentinization is maximal. You sort of have competing effect. The higher the temperature, the faster the chemical reaction, but the higher the temperature, the harder it is to get fluids deep. So there are trade-offs. And in any case, yeah. Okay, so now we have this picture where we have the ocean crust that's heavily serpentinized. You know, I never asked, by the way, how long should I talk?
You calculate half an hour.
I have half an hour more?
Yes.
Then there's absolutely no problem. I'll try to make sure I give you time for questions. So the ocean crust at mid-ocean ridges is hydrothermally altered, associated with the black smokers. A little bit of serpentinization at mid-ocean ridges and more where you have ocean core complexes at slow-spreading ridges, or especially fracture zones at slow-spreading ridges. And then when the plate starts to bend, you have general serpentinization associated with this Bend-Faulting that leads to this partially serpentinized uppermost cold mantle. And then as the slab goes down, this progressively deserpentinizes. And as well, the ocean crust and sediments lose their fluids. And yeah, and the plate is bending here, and the plate is unbending here. And so the first thing I'm going to talk about is I think this is actually related to how the plate bends and unbends. So we all learn now in earth science that when the plate subducts, it bends. We learn about the outer rise that was discovered from it was discovered in the 1930s. And because it happens, we almost are just taught this thing like it's obviously, since it happens, it must happen, which is true. But mechanically, this is actually really, really difficult. And I can show you, well, I will show you, that it's theoretically impossible. So if you have a plate that doesn't have some interesting mechanical transformations, it's actually impossible that it could bend and unbend. So with the standard theories to make the outer rise, there are 2 of them. One is that this is an elastic plate flexure, and I think the elastic part has to be true. I'll show you a picture in a second why I think so. But in fact, for most trenches, a viscous flexure could do the same thing. Okay, now why I think it has to be true is that here we can see the outer rise with its strong gravity signal. And in the case of the Aleutians, we can see an outer rise. This is the Hawaii Emperor seamounts coming in, but it's fairly persistent. If you look in there's another beautiful example that I don't have here, which is you look at the Puerto Rican Trench in the Caribbean, that you have almost a transform fault where Puerto Rico and Haiti, Hispaniola are. And right where the transform fault is, that the seafloor is moving this way, you preserve an outer rise. And so basically, you have more than 10 million years, and 25 million years for Puerto Rico, that you have a permanent bulge. And if you had a viscoelastic material that was the plate, the relaxation time of this viscoelastic material would be proportional to the viscosity of that plate and its elastic, some elastic property like the Young's modulus. We know the elastic property really well because it's related to the speed of seismic wave propagation. If this is more than 10 million years, that means we know that this viscosity has to be more than 3 times 10 to the 25 or 10 to the 26 in order to be able to keep an outer rise bulge for 10 million years. Or alternatively, in order to keep what you don't see very well here, but there's a small bulge related to the load of the Hawaiian chain on the lithosphere, and that too is preserved for tens of millions of years. So the Pacific lithosphere, the oceanic lithosphere, is at least near the top having a viscosity that's very high. And yeah, okay. So now we go back to the classical model. Not only do plates bend, but if you think about these wood carvings, unlike wood carvings where you take a knife and you scrape the wood and you make this little thing like this, the plate also unbends, and it unbends much deeper. And this is under a really high confining pressure. So a material that is either viscous with the right with a high viscosity, or a material that's elastic plastic and slipping on faults, it is almost impossible to unbend this material. And in fact, this is a numerical model that put in a viscoelastic rheology with an elastic plastic yield strength. And Marie-Pierre Douin gave me this a while ago. And in her model, she had a perfectly good time of making plates bend. But you can see that this self-consistent model didn't make something that looks like a subduction zone. Okay, so we can analyze this for a viscous deformation, that we have a plate coming in and then bending and then bending here, unbending here, and coming out. And the only thing I want you to get remembering is if the viscosity was 10 to the 25, and in fact this is a fairly slow speed of 3 centimeters a year, you use up 10 to the 13 watts to bend plates. We can do the same thing for elastic plastic, where the yield strength is increasing with pressure, with overburden, and we use this so-called Christmas tree kind of envelope. And again, we bend it by straining it, and I'm just making a very crude approximation that we have a perfect, just uniform stretching, maximum at the top, 0 at the midplane of the plate, and the opposite the other way. And we can evaluate the work done to bend it and to unbend it. And again, I'm sorry I didn't make time to clean up this slide, but this estimate is also saying something like 10 to the 13 watts. And the reason that 10 to the 13 watts is important is that if you take ocean lithosphere and you know how dense it is near a subduction zone because you know how deep the seafloor is. So you know the density anomaly between the oceanic lithosphere and the average mantle, the asthenosphere. You take that density difference going in at the speed that the plate is going in, and you release this potential energy by bringing it even all the way to the core mantle boundary, And if you do that at present subduction rates, it releases 10 to the 13 watts. So if it takes 10 to the 13 watts to bend a plate or more, and if you only have 10 to the 13 watts that's driving convection at the current rate, that the potential energy release of a dense plate sinking to the bottom at modern rates is it's releasing 10 to the 13 watts. If it takes all the energy there is and a bit more to bend the plate, it's basically thermodynamically impossible to have mantle convection. But obviously, the answer is definitely that some important physics is missing. Something's wrong in this estimate. And I think what's wrong is probably linked to this serpentinization. So either plates have to behave much weaker when they actually bend and unbend, or you need another energy source to cause the plate to expand when it bends and contract when it unbends. And I think serpentinization does both. It does both because serpentine is weak. Serpentine is known to be much weaker and actually have a very small pressure dependence of its yield strength compared to peridotite. So this would make it mechanically much easier. But serpentine also has this huge volume change, which is working the right way. That if we have expansion by 10 to 20% serpentinization, that expansion will basically just cause the plate to, that's the bending. And then as the deserpentinization happens, and in fact, as the ocean crust transforms to eclogite, which is also a denser phase, that will tend to pull the plate and make it unbent. So the picture I have is that this is what's actually making plates bend and unbend. We really need water to make it happen. We need water that the plate is allowed to bend, because as bending starts, the faults happen and serpentine fills those faults, and it also makes faulting easier. And then unbending, as you go down and the pressure is high enough and it heats up, those partially serpentinized regions lose their water, and you get contraction. And so then it doesn't take, that's not needing much work at all that's related to the forces driving plates to make it happen. Okay, so now the second part, and there will be time, is I think this also may have big effects for the carbon cycle, as well as the water cycle, or maybe volatile cycles in general, and maybe even magnesium. This is now another question. So what we're making a picture of here for historians, we are basically resurrecting an idea that was prevalent in the 1960s, that was the preferred hypothesis of Harry Hess. When he thought of seafloor spreading, he actually suggested that what we now see as the ocean, this is his cartoon of a mid-ocean ridge, what we see now mostly being basaltic ocean crust, he thought was actually partially serpentinized mantle. And so in the 1960s, there was a period of time when people really studied serpentine intensively. And basically in the early 1970s, the petrologic community convinced themselves that instead the ocean crust was mainly basalt, the so-called Penrose crust. And after the early 70s, studies of serpentine were very much on the back burner until the 2000s, I would say. But so he had a layer about 6 kilometers thick of partially serpentinized mantle. In this picture here, we're having a layer that's up to 10 or 15, 20 kilometers thick of maybe somewhat less partially serpentinized mantle, but about the same amount of total serpentine. It's just that we're forming this as the plate is bending, instead of forming it at a mid-ocean ridge and bringing it to a trench. And this happens to be a picture of the first serpentine that I saw growing up, which is just the steps in the geology building at Princeton. And the gray, or the white in these steps, is basically carbonate. So serpentine contains an awful lot of carbonate. And people who know this will say that I'm being a bobo for even sounding surprised. But there's a name for this. They're called ophicalcites. You basically, wherever you see the nice green of serpentine, you often see veins of white within it, and the more white, often the more decorative it is, so it gets used for buildings and steps and things like that. And here's a nice quarry in Italy that has it. Here's a fault zone in an ophiolite in Norway that has actually converted to soapstone, which is a magnesium carbonate that's not serpentine, but it's even beyond, if you will. And then here are just some other pretty pictures of carbonate-related serpentinization hydrothermal systems. These are actually at mid-ocean ridges, but the venting is coming from a serpentine-hosted hydrothermal system, and it's precipitating calcite like, well, in this beautiful way. At mid-ocean ridges, when you have serpentinization, which you absolutely do, where peridotite is exposed near the seafloor, we find on the order of about between 0.5 and 1 weight percent carbon dioxide in normal mid-ocean ridge carbonated peridotites. So Peter Kellerman wrote a very nice review article, now it's 4 years ago, co-wrote an article, and basically documenting that you have significant carbonation at mid-ocean ridges. Serpentine is associated with conditions that really favor the precipitation of carbonate. So the big question, basically, a big question, is how much carbonate precipitates when you have Bend-Fault serpentinization? Is it 1%? Is it 10%? This stuff here, it's more like 35%, but this is picked by humans for its interest. Now, just to do the numbers, a 1% carbonate fraction in a 10% partially serpentinized layer, so that's what we are seeing conservatively in Nicaragua, and make it 10 kilometers thick. That's also what we're seeing in Nicaragua, where the seismic multiple comes in and you can't see it deeper than that there. But in Japan, or the double benioff zone, it's often 30 kilometers thick in old plates. It's much more than 10. 1% carbonate of 10% partially serpentinized mantle, 10 kilometers thick, ubiquitous at subduction zones, that's the assumption. That's enough carbonate that 40,000 years you would use up an atmosphere of CO2. So this is a flux that is like the flux at mid-ocean ridges. It's a pretty big number. And in particular, this carbonate associated with Bend-Faulting could be larger than the carbonate that's in the overlying sediments and the ocean crust. And it would be 10 to 40 times more than the carbonate that's trapped associated with the ridge serpentinization that Peter Kellerman talked about. So with this, it's definitely more than 1. That's that conservative estimate that I showed you. Maybe on the order of 4. It's a significant large-scale flux of carbon that could be entering the mantle at subduction zones. It's probably larger, in fact, than the outgassing at ridges, and this is why I'm strongly suspicious that we're going to find that there's more net outgassing at ocean hotspots. That's not included in this. I suspect we're going to, in our revised scenario 10 years from now, I wouldn't be surprised if ridges are said to be 2 and hotspots are said to be 2, and Bend-Fault serpentinization is said to be 4 to 6 going the other way. It still is relatively small compared to some of the larger scale surface fluxes, and this is why I don't think it was discovered from first principles. I mean, this is the kind of number. If this was an order of magnitude bigger, we would have had a known deficit that no simple model now with bad parameters could be made to fit the global carbon cycle. You can make models that fit the cycle and ignore this, because it's the same flux as some of the other uncertainties in the whole picture. But still, compared to ridges, it's big, and it's associated with the subduction process. right now, in terms of science, I think the real priority for Bend-Fault serpentinization to become active, to become something that people start investing a lot of money, is we have to find the hydrothermal vents that are in this system. I think if we find vents and we find vent communities, then we will find stronger scientific interest from a broad spectrum of marine scientists, and we'll find stronger public interest from people that think it's amazing, the systems associated with deep sea hydrothermal vents. For me, there's strong geophysical evidence that it exists, and the evidence, for example, in Nicaragua and South America, is that we can measure the heat flow in these areas. There's been a few measurements of heat flow, and where it's been measured offshore Nicaragua, it is always about 10 to 20% what the theoretical heat flux should be for seafloor of that age. So the fact that we're seeing really low heat flow when we randomly probe it is suggesting that there's a fairly strong inflow of water into this system. And these lines here that you don't have to worry about, these are the lines for if you had water just going in to make a reaction and then being lost to the chemical reaction. So if you had water only going in and not coming out, you would expect a reduced heat flow in both Nicaragua and off Chile, but it would only be 60 to 80% of the heat flow for seafloor of that age. And the fact that it's 10 to 25 is saying we have a strong component going in and most of it's coming out again. So we really have a system that's going in, reacting to make serpentine. It's an exothermic reaction, I didn't mention that, has a 300 degrees Celsius latent heat release, the complete reaction. That's driving upwelling. And so I really think there should be vents. They will not be probably as spectacular as at mid-ocean ridges, but they should exist along these faults. Here is an example, same area in Nicaragua, where there was a little seismic study done, again by the Geomar group. And in this area, they locate earthquakes that look like they're sitting right along bend faults. So there's active seismicity, there's probably active fluid flow. This, I'm picking a picture from a mid-ocean ridge. I think we should see seeps on the seafloor there. And in the Guatemala Trench, which is a little bit to the north of the map that I showed you, there actually are a few little features right in the axis of the trench that are hundreds of meters high, that multi-beam, bad C-beam kind of bathymetry can actually see. And these pinnacles may well be extreme examples of this kind of thing. But the usual much smaller vents or mid-ocean ridge-size vents, you wouldn't even see with the multi-beam imaging that we have. You'd have to get closer to the seafloor to see it. Okay, so that's it. I really just wanted to share this idea that I think is likely to be significant. I think if this process really exists and is as important as it might appear to be, it's going to have some fairly big implications for the life forms that are associated with this hydrothermal system, with the carbon and water budgets of the deep cycling of these volatiles. It may actually be creating a geochemical reservoir, this carbonate that is associated with serpentinization, yeah, I'll leave it there. So thank you very much.
Thank you very much. Any question, please? Yes.
Okay, so I have a question, but it might be multiple pronged. How do you actually envision the way water flow through this system? Because the way you put the math, it looks like you're talking about quantitative removal of water, but that would imply that you also have a quantitative removal of everything else.
Yep.
And if you have a quantitative removal of everything else, then you should also remove sulfur, magnesium, calcium, sodium, and chloride, which don't exactly appear, that would appear to form their secondary minerals within the system, and not necessarily.
I think that's actually a really open question, and I don't have, I'm trying to see if I have a better picture. I don't think I have a better picture. Just these faults here, I think the hydrothermal systems along these faults are associated, the scale here is a bit too small, but associated with downflow along most of the fault, and then upflow along the same fault. So in other words, we have to do a three-dimensional picture, that we have a distributed feeder zone. Well, it's almost a two-dimensional picture, that the fault has a lot of low-scale inflow, and that's why heat flow measurements on the fault that are random just are detecting the inflow. And then you have these vents and seeps where it's coming up, and below the blowhole, you have this reaction zone where the water is much more, there's much faster, higher reactivity when the water finally gets into contact with the mantle rather than the crust. So there's the serpentine reaction. When I say quantitative uptake of water, the serpentine basically wants the oxygen, the hydrogen, and the chlorine. I mean, those OH bonds, those OH molecules are behaving chemically, or chlorine or fluorine, are a big part, they fit well in the bond sites in serpentine. So it doesn't want, necessarily, it doesn't want so much but you would really have to look at it. And I suspect people looked at it a little bit, again, in the 60s. And I don't know if people have looked at it yet in the modern era. What the chemical what happens to these associated important elements in that system. So how the composition of seawater is modified by reacting through
because we know, for example, magnesium is getting stripped out in white smokers and black smokers. It's not there.
Mm-hmm.
But we do get calcium, and we do get carbon in there. So we don't have quantitative removal of carbon within the system's unreached flanks. And here we are a lot colder. So it's unlikely that we're outstripping as much, at least in respect to ions like to the common ions.
Well, these faults, the rate. So the plate here, this here is about. Well, here's the scale that I can't read, but I suspect this is 10 and 11. 11, I can't read it. Okay, this here is 40 kilometers. This red bar here is 40 kilometers. The outer rise here, the Bend-Faulting really starts about 100 kilometers, 120 kilometers from the trench, so right around here. And it takes about 1 million years to get to the trench, 1.5 million years. So unlike mid-ocean ridge systems, these faults are active for a longer period of time, meaning maybe a factor of almost 10 longer. They are definitely colder where the reaction's happening, and I don't have answers to your questions.
Okay.
Okay, thank you. Yossi, please.
In analog experiments of subduction, we managed to drive the oceanic lithosphere under the continental lithosphere, but not into the upper mantle, not to the asthenosphere. And we reasoned that serpentinization would take place together with the acclimatization. So some part of the downgoing slab will become denser, and other parts will become lighter and will go up there empirically.
I think what you're saying is really an important mechanical problem. The picture that I have of this going down, one of the things when you do these models of thermodynamic models of taking the sediments and the ocean crust and the mantle and trying to bring it down a thermal structure that's consistent with a subducting slab environment, where the slab here is being heated up because the overriding mantle wedge is hotter than the slab. So it's being heated from the top as well as being heated a little bit from the bottom. In that situation, in fact, the sediments lose most of their water fairly shallow. They dehydrate temperatures less than 400 degrees, and the top of the slab is the hottest part of the slab system. And the serpentine core is actually progressively getting warmed up as it takes time for heat to conduct 10 kilometers into the slab from the top. But so I think the sediments and such lose most of their fluids here, the ocean crust a bit deeper, and in the area right under where the arc melting is happening, what you're mainly having is volatiles being released from the serpentine that has just starting to dehydrate, and it's busy passing through this system, and it's also reacting very well, and this stuff is reacting as well when the fluids get released initially, with the mantle and the overriding wedge, and making a new layer of serpentine that's on top of the downgoing slab that is the subduction channel. So you are feeding a lot of fluids through the ocean crust and possibly reacting through the sediments that have already dehydrated and possibly even causing them to melt, and into this mantle here making serpentine. And so as the eclipsization is happening, which is also happening about 80 kilometers depth, it's right in this region where you can be making new serpentine at the top of the system from the fluids released by this older serpentine. And so you have a subduction channel where you have sediments, ocean crust, you may start even having little bits of diapir, I don't know, but along these faults, and especially on the top, you have a lot of serpentine, and that's what comes up in many of the alpine sutures and such. You're seeing stuff from the top of that channel where you have eclogite blocks mixed in with serpentine.
Yes, and the serpentine bring the ultra-basic to the surface.
And the serpentine is low enough density to really bring that higher density stuff that the average density is relatively low.
And furthermore,
Sure.
I would say that the quantity of serpentine that's being produced will reduce the friction between the slabs. So the more serpentine you have, the less friction you have, and different styles of subduction.
I don't disagree at all. And one of the paradoxes that people know is that in very crude subduction models, if you put a coefficient of friction in this system in the old days, you get too much, again, mechanically, you get too much shear heating. So people have assumed for a long time that this whole region along this interface, almost all the way down to where the arc is rooting, is very, very low friction. And I think serpentine is an obvious candidate for why it's so low friction.
Okay, so just because last question from me is because in the modeling of the subduction, this is artificial lubrication done, which is probably created by the serpentinization.
So I think in the subduction process, you have lubrication at the top and lubrication along the subduction channel from the serpentine that's at the top. You have the swelling of this plate, like think of your cutting board in the kitchen when it gets wet and how it bends. So you have the swelling of this plate that's helping it to bend, and you have the loss of the fluids at the top of this plate that's causing it to unbend, and all of this is happening in a sense because of the reaction of water with mantle. It's all linked to serpentinization processes. So a dry planet, maybe this doesn't happen. Like Mars or Venus, for example.
Okay, thank you very much for your time.